So today we talk about the hashing. So the topic is applying the hashing method for multimedia computing. Okay, so today's outline. Maybe we will spend 2 weeks to talk about possible hashing technique and its applications. And I will also review some recent papers using hashing technique. Okay, so first I'll give an introduction for what's the hashing, the motivations, purpose. This is a general idea. And then we will have 2 subtopics. First is we use hashing for mining and index your data. Okay, including the single mean hashing and the locality sensitive hashing. And the second subtopic is we use hashing to do the binary embedding. Okay, so this means we use the hashing function to convert your document. Can be a text document or image or audio. Convert these documents into a binary code. And we will introduce some famous popular method like LSH, ITQ, and some deep learning based method. Okay, so first I'll give an introduction for our hash function. Okay, so hash function is a function that can be used to make arbitrary size data to fixed size data. Okay, so here is an example. So you see we have several names. Okay, these names we can call it their keys. Okay, now we want to convert them into hash values, or maybe like these personal IDs. Okay, so here we prepare a hash function. So the hash function now it looks like a black box. Okay, so give any keys like it's several words. Okay, it can be arbitrary the size. So for example, the John Smith. Okay, so take it as input. Throw the hash function, it will generate a hash value. In this case, it's 02. And the second name is Lisa Smith. Okay, you can see their size are the same here, the same to the John Smith. Okay, but because its alphabet, its characters are different. So you can see through the hash function, each hash value becomes 01 here. And the third name is Sendo. You see the size are different. Are different to the previous 2 names. Okay, and through the hash function, we generate the hash value 04. And the last name, Sandra D. Through the hash function, it generates hash values 02. It's the same to the John Smith. Okay, so it means the hash function generally, when you give a different names, I will give you different hash values. But sometimes, because of the design of your hash functions, maybe we will cause some collision. For example, like this, the John Smith and the Central D's, they generate the same hashes, although they have different names, but they generate the same hash function. We call this situation, this collision. Okay, so this is a general concept of the hash, and this idea is widely used in cryptography and database areas. Okay, so for example, in cryptography, we use it to encode your original message into a secret message like this. So it's difficult to know. Okay, give you the hash value, but actually I cannot invert to your original message. is difficult. Because I don't know your hash function, so it's difficult to inverse it to its original message. Okay, so you can use it to the cryptography or in database. In database, you can use it to generate your keys to a unique ID, but sometimes it generates like a collision. So in database design or in cryptography, we usually hope your hash function should generate a unique ID, generate a unique hash values for each different keys. Okay, so any problems? Okay, so but in today's topic, we will talk about how to use the hash function to find a similar set from a data set. So from the previous example, you can see some keys. Some keys like John Smith and Central Disk, they can generate the same hashes. So although we don't like such situation because of the collisions, but if we change to a different area, like we want to find a similar set, okay, we hope to find the collision from the hash functions. But the collision means these two data are similar. So if they are collisions, we can use these characteristics to find the similar set from your data set. Okay, so the idea can be applied in several applications, such as data mining, near duplicate detection, clustering, recommendations. All these applications, we want to find similar sets. Okay, so we can use this idea to help us. And hashing has this unique characteristic because it can be very compact. So generate a hash code can help us to find the similar set efficiently. And here I list a reference. Okay, you can refer to. It's a 20 years ago's paper. Yeah, but it's still, these ideas, this concept is still useful. Okay, finding interesting association. Okay, so today I will introduce some important technique used to finding the similar sets. Okay, including the 3 techniques. First, the shingling. Okay, the shingling idea is to convert your documents to a feature set. Okay, it's a very easy, very simple idea, widely used in NLP area. Okay, now today we can use some LLM encoders to generate features. Okay, so now, but before that, in past years, actually the shingling idea is very it's widely used and easy to apply. And the second technique called min hashing. Okay, the min hashing is try to convert your set, your feature set, to a short signature. So it's a more compact, but even it's compact, it's a short signature. It's still preserving the similarity between 2 documents. If they are similar, okay, after they convert into their min hash signatures, their signatures are still very close. Okay, the third technique is called locality sensitive hashing. Okay, this idea is try to improve the min hashing. Okay, to give a very good index structure so that we can find the similar signature very efficient. Okay, this is our pipeline, how to apply the three techniques. Okay, so that we can find the similarity set in a very big database. Okay, here is our document set. So each document, we will use the shingling technique to retrieve, to extract its features. So here, suppose we generate a landscape features. Okay, so to generate a feature set, and then this feature set are through the mean hashing technique. Okay, this technique is try to generate a short integers from the previous shingling set. Okay, so but it's still we want to keep can reflect their similarity between any two documents. And then finally is the locality sensitive hashing. This idea is to build an index structure so that we can find candidate pairs. The candidate pairs means we expect they are highly similar, so we can find it very, very fast. Okay, any problems? Okay, so first is shingling. Okay, shingling actually in NLP we call it n-grams. So n-grams works like this. So here is a sentence, a document. A rose is a rose is a rose. Okay. So for this sentence, we extract the shingle or n-gram. You can imagine that we have a sliding window, and the window size is 4. So first we put the sliding window from A, from the first character. Okay. And then what you can find is the first shingle rose is there are 4 words in a window. Okay, so then we move forward our sliding window to next character. So the next shingle is rose is a rose. So each time we just extract 4 words in a window. Okay, then we continue. So next is rose is, and then rose is a. Okay, so we can continue to check all the shingles. So here we can see there are some shingles that are the same. You see, a rose is a, and this one is also a rose is a. So they are the same shingles. So but we don't mind the frequency because in this way shingling is just a backward-words model. So we call it backward-words model. We just count how many different words appear, but we don't count how many times it appears. Okay, so just count how many different shingles to be shown in the document. Okay, so then based on these n-grams, so a document can be represented by a set of shingles. This is a shingle. The first, second, third. This one is same as first. Okay, so in this case we generate here. There are 3 different shingles. Okay. And after we track the shingles of any 2 documents, so here we want to measure the similarity between the 2 documents, CI and CZ. Okay, and each one we use the previous method to retract. Okay, let me show you. Okay, first we want to retract some features from the documents. Okay, so here is a very simple ideas for the shingles. Okay, here is an example, a sentence here. A rose is a rose is a rose. So we have a sliding window, and the window size is 4. So each time we just use the sliding window to track 4 words in this sentence. Okay, the first word is first sentence is first shingle is rose is. Then we move forward the window. So the second shingle is lost, is a loss. Okay, and the third is a loss. So this is the way we track the features from each document. Okay. Then we track several shingles and for two documents, Chih-Yi and CJ, each one we already represented as a set of shingles. And how to measure their similarity? So here we use the Jacob coefficient. The Jacob coefficient is expressed like this. You can see the numerator is Chih-I and the intersection is CJ. And then the denominator is Chih-I union with CJ. Okay, so you can see here is an example. We have two documents here, and for the left document, you can see the left circle. The left circle we have 1, 2, 3, 4, 5 points. Each point represents a shingle, a unique shingle. And also we can check the right circle is the second document. And the second document we have 1, 2, 3, 4, 5, 6. It contains 6 shingles. Okay, then how to measure their similarity? Okay, the idea is we can measure their intersection divided by their union. So in this case, how many shingles they have in common? 3, right? They have 3 shingles they have in common, right? Okay, so their intersection is 3. And how about their union? The union will be the complete, how many unique shingles in total. So you can count, there are 8, right? Okay, so based on this, you can compute the similarity. It's a union, it's an intersection divided by the union. Okay, so it's a 3/8. So it's what we call the Jacob coefficient. Okay, it's a very simple computation to measure the similarity between the two sets. Okay, any problems? Okay, so now we can convert the set to a Boolean matrix. Okay, so here you see we have a C1 and C2, 2 documents, and each column represent is like a binary vector. The binary vector indicates if the C1 document contains this shingle, we use 1. Indicate it has this shingle. Otherwise, we use 0 to mean this document doesn't contain this shingle. Okay. So for C1 document, you see, you just check this first column here. It means C1 document has the second shingle, third, and the 5th shingle. Okay, and for the C2 document, you check the second column here. It contains the first, third, 5th, 6th shingles. Okay, so we can represent the set, your feature set, your shingle set in a binary form, like this. Okay, so if we convert your shingle set into a binary matrix like this, so we can compute the similarity in a similar way. Okay, so you can see we just check how many we can check the intersection or the union from this matrix. So the Jacob can be computed. like this. Okay, here you can, in Jakarta's coefficients definition, the intersection, their union and their intersection can be calculated by if they appear, then both shingles appear in the two documents, like this. For example, in the third shingle, they appear in both documents. You see? Okay, so their intersection is in the third shingle and also in the fifth shingle. Okay, so their intersection will be 2 here. And how to calculate the union? You just check the 0, 1 or 1, 0 pattern, and also 1, 1 pattern. Okay, you can count the first row, and the second row, and the third row, and the fifth row, and sixth row. In total, there are 5 rows. Okay, so you can count the union here. So this is another way, and we can treat the Jakarta coefficient in this way to do the computation. Okay, you just count how many patterns appear 0, 1, 1, 0 appear in between the two documents. To compute their intersection and the union. Okay, any problems? So it's provide you another view to calculate the Jakarta coefficient. Okay. All right. So, but this idea, if you convert it into a Boolean matrix, and you use this matrix to compute the set, intersection, or union, actually it's very expensive. Why? Because your number of rows is usually very large, and your number of columns is also very large. See? So you can see you will contain many shingles. Even you compare only 2 documents, the number of your shingles equal to your number of rows will be very large. Maybe just 10,000 or 100,000. It will be very large. So to solve, to find or to generate such a Boolean matrix, or to compute the Jakarta coefficient is inefficient. Okay, so this is our idea. So maybe we can generate a compact representation for each shingle set. Okay, so next we will talk about how to compute, how to generate we call the shingle, from the shingles to signature. A signature usually means a very compact features. Okay, we use it to compute to the similarity between the documents. Okay, so that's why we introduce the second technique called the mean hashing. Okay, the mean hashing, the idea is to create a signature vector for each document from the shingle set. Okay, it's a formal definition here. For the document C, we want to generate its ith signature. Okay, we represent like this. Okay, for the ith signature, and here we define f is the hash function. It will make the shingles into a universe from 0, 1 to the 2 to the n. And second, we will use another random permutation function called the pi. The pi I will commute all these your shingles number, your IDs. Now we commute again, map to the same universe, but they are randomly commuted. And then at the third step, we will pick the minima one. After your permutation, we pick the minimum values as your signature. So it's pipeline how to generate the signature for the document. Okay, so this is why we call it a min hash, because we pick the minimum hash values from this function, from the permutation function. Here I show you an example. Okay, so given a document 1, C1. The document C1, suppose we check 4 shingles. Okay, there are 1, 2, 3, 4 shingles. And each shingle we map it into a universe from 0 to 2 to the 64. Okay, so you can see now we have use a hash function to map each shingle to this universe. Okay, so this universe is exactly like a 64-bit universe. So it means each shingle is encoded, can be encoded by a 64-bit binary code. Okay, so it's first step. Okay, equal to this one, the first step. And then the second step here, we will do a random permutation. The random permutation is, you can see this is our first shingle, but after random permutation, this new position is here. And then the second one is to commute to this new location here. And the third shingle is commute to here. And then the fourth is commute to here. So you can see the blue shingles now is randomly commute to its new position, to the red position. Okay? Okay, so you can see the third row here is a new position. After the permutation, each shingle get their new position. We just pick the minimum one as the min hash. Okay, any problems? It's very simple step. Okay, so 每一次就是有一个虚构，就是先产生用一个 hash function， 好，先产生这个虚构的这个 hash 的值，好，这是第一个。然后再来每一个虚构呢，它会随便排一个位置，好，就在原来的这些空间上面，原来这个 universe 上面，就随便给它一个新的位置，就叫随机排列。好，随便排一个新的位置，得到一个红式的值。那这个红式的值就是排列后的一个新的值。那这边有4个新的值，就选最小的一个。好，这个就叫 min hash。好，所以为什么叫 min hash 就这样来。So, but with the same idea, you can also design a new idea called the max hash. This means you just pick the max one. And but the effect is the same. The same effect. So here we just talk about the min hash here. Okay, so it's for the document 1, the C1 document. Okay, we use the min hash technique to generate this min hash value here. And for the second document, okay, we can repeat the same process. Okay, we generate, it also contains 4 shingles. And each shingles we do the random computation here and also pick the minimum one as the min hash value here. So, okay, for document 1 and document 2, we will get a different, I'm not sure, maybe they are the same. we get two mean hash values A and B. So what's the probability they will have the same mean hash? Okay, so here is the question. If A and B they are equal, so it means their shingles with after the computation and extract the minima values, they will be the same. Okay, so what's the probability? The probability will be the same to Jacob coefficient of the two documents. So it actually can be represented like this: the size of the intersection divided by the size of union. So the probability A and B will be the same. It's the same to the document similarity computed by the Jacob similarity. OK， 好，这边的意思的关键是说 ，document one 的那个mean hash值跟 document two 的mean hash值，它们两个一样的几率等同于是 C1 跟 C2 这两个相似度。它们相似度越高，它们的那个 mean hash 相同的几率越高，是一样的。Okay, so let me say again, the general idea you should take away today is the probability of the mean hash A and the mean hash B, they are the same, is equal to the similarity between the document 1 and document 2. Computed by using the Jacob similarity. Yeah, maybe you think it's very weird, right? Yeah. How do you know they will be the same? And the probability just the same as their similarity. Yeah. So let me explain why they are the same. Okay. So let's go back. We go to the binary matrix here. Okay, you see? And here there are 4 different types of rows. First is, you can see I have A, B, C, D, 4 different rows. The A rows is 1, 1, like this, 1, 1, 1, 1. This belong to A row, row belong to the A type. And the B type is 1, 0. You see, 1, 0, here, 1, 0. And the C type is 0, 1, 0, 1, here, and also here. And the D type is 0, 0. 0, 0 is here, you see. So from the primary matrix, you can find 4 different row types, right? And here we claim that, okay, we denote here the A's cardinality is represented as the number of the rows of type A. So in this case, how many? The number of the type A is 1, 2. There are 2, right? 2 type A's rows. Okay, so we reduce this notation. Okay, it means the number of rows of type A. And the Jacob coefficient can be computed in this way. Okay, your numerator is the number of the rows of type A. You see, there are the first one, the second one. So you have 2 type A. And your denominator is here. It's A plus B plus C. Actually, it's the type A, type B, type C. The total number of these 3 types. Okay, so here you see the type is belong to type C, and type B, type A, type A, type C. So in total here we have 5. right? And we don't count the 0, type. Okay, do you agree? The Jacob coefficient can be calculated by using this. Okay. Okay, then we do the random permutation. Okay, it's a very key, very important key point. You have to do random permutation. Okay, random permutation means I will change the nodes between them. For example, maybe your 6 nodes is shift to the third, and the third move to the first move to the second. Just random, we permute the nodes orders. Okay, this is called a random permutation. Okay, and then after we do the random permutation, here we define a function like this. This means the h of Ci equal to the index of the first row is 1. What means the first row is 1? When you check this column, the first row with 1 is here. You see, this for the C1 document, the first row with 1 is the second row, right? So its mean page will be 2. Okay. And for the C2 document, its first row with 1 is the first row, right? So its mean page value will be 1. Okay, it's very simple, right? So it's called a mean page. It's ideal to call it a mean page, but you have to permute. After the permutation here, then check from the first row to see if the 1 appear. Okay, so you see the first 1 appears at second row, so its mean page will be 2. And we say the property here, the mean page between the two documents is the same to the similarity between the two documents. Okay, fine. Okay. Both are the same to this. Okay, I think we know the Jacob coefficients compute based on this. Right? No problem. Okay. But why the mean page values, they are equal? The probabilities of this probability is also the same to this. Why? Okay, so I think we can imagine that it's like to perform a lottery. Okay, so here we have I take this as an example. Okay, so we have 6 rows here, okay? And each row we only deal with we will ignore the 0, row. We ignore it, and there are 5 rows. Okay, it's the first row, the second row, the third row, and we ignore the 0 here. We don't count it. And this. Okay. We can avoid this, right? And we can treat it as a special bank, or it's a special bank here. And all we can treat is like a ball. Then you will have 5 balls. And each box will give this ID like this 0, 1, 1, 0, 1, 1, 1, 1, 0, 1. And we put all these balls in a box and then randomly pick 1 to do the permutation. So it means maybe this one will be, it's like to play the lottery, right? There are 5 balls and then you just you will pick 5. And suppose the first one you pick is the first one you pick maybe this one. You pick this one as your first ball, and the second ball maybe like this, and you just pick any. You just pick 5 balls. It's like we call the permutation. Okay. Okay, so I just list all of them. Okay, I pick 5 balls, and I want to ask you, what is the probability if your first ball is 1-1 from this box?
40%.
40%. So same to the Jakarta coefficient, right? Got it. Okay, so any problems?
This communication methodology is used in lots of memories and
And yes, so in practical we will not implement in our program like this. But if we want to illustrate our idea concept, okay, we say we need the communication. But in implementation we will use another way to simulate this process.
Because the notation when you can
Yes.
not apply
Yes. Yes. So we will later I will tell you another implementation trick to how to simulate this implementation. Yeah. Okay. Any problems? Okay. So just look down. Okay. So until you find the first non-type rows, and you will find the probability they are the same. The mean hash are the same. It's actually the type A rows. How many type A rows in your box? Okay, so let's tell you more details about this. Okay, so we can follow this idea, and we can generate k random row permutations. So this means, for example, 100 times. Okay, so this means you have to do the 100 permutations, and if the number of k is large, the more times the less error. Okay. Okay, so then your mean hash signature can be represented like this. Okay, the signature I is a list of the k index of the first row with 1 in column Ci. For the ith document here, its signature is a list of k mean hash values. Okay, the k mean hash values is just to perform the k random permutations. But also you can use k hash functions and perform k permutations to generate your k mean hash values. And the similarity of the signature can be expressed like this. Okay, so its expectation E, okay, between the two signatures is also the same to the Jakarta coefficient between the two documents. Okay, here I show you example here. Here we have 3 documents, C1, C2, C3. And each document, we have 5 different shingles from R1, R2 to R5. Okay, now we try to generate 3 mean hash values. Here we have prepared 3 permutations. The first permutation is the order is 1, 2, 3, 4, 5. Okay, so this means we just keep the same order here. We don't random shuffle it. Okay, So you just follow it 1, 2, 3, 4, 5 to check the first one appear in the document. Okay, so for document 1, please check the first column. We check the order from the row 1, row 2, follow this order. 1, 2, 3, 4, 5. Okay, so you can see the first one appear is at R1. Right? Okay, so that's why here is the main hash value is 1. Okay. And then we check the second column, document 2. We check from the order R1, okay, it's 0. Okay. R2 is 1. Okay, so we put the mean hash value here 2. And for document 3, the R1 is 1. Okay, so it's mean hash value is 1. Okay, this is for the first computation. And then we want to generate the second mean hash value. Okay, we use the computation tool. The computation is 5, 4, 3, 2, 1. The order is reshuffled like this. Okay, so it means you have to check this matrix from this order 5, 4, 3, 2, 1. Okay, so the first we check the document 1. Okay, the is 0. Okay, so we skip. The next R4 is 1. Okay, so here we keep the first mean hash appear at R4. So 5 plus 5 is mean hash value is 4. Okay, we will follow the same step for the second document. You can check. Its fifth row is 1. Okay. So here is 5. And for the S3, for the third document, we check the third columns here. And from the R5 is 0, R4 is 1. Okay, so here, give 4 here. And for the third computation, is 3, 4, 5, 1, 2. Okay, we have to check in this order 3, 4, 5, 1, 2, like this. Okay, so you can see the first column is 1. Okay, so we give here the mean hash value is 3. And for the second document, okay, we check from R3, R4, and R5. You get the first one appear. So here, R5. 5 is the mean hash value. Okay, so for the third column, we check from R3, R4. This one, the first one appear. So that's why we make it later. Mean hash value is 4. Okay, so we follow this idea to generate the signature, the mean hash signature from the, it's a simple case. Okay, but now we use the computation, mean hash, some hash function with computation, we generate the signature, we call the mean hash signature for each document. And we want to compute their similarity. Okay, it's easy. So if you compute the similarity between 1, 2, between the first and the second document, what will be the similarity? We can compute from the Jakarta similarity from here, and also compute the signature, the mean hash signature from here, and we can compare are they close or not. Now we check the first two columns, the C1 and the C2 columns. What is their Jakarta similarity? You see? 0, right? Okay, their Jakarta similarity is 0 here. It's column to column. Jakarta similarity is 0. And we also check their signature similarity. Signature similarity is here. You check the first two columns. Okay, just compare are they the same or not. Okay, here, okay, all are not the same. Okay, so the similarity is 0. Okay, so both the color similarity and the signature similarity are both 0 between the document 1 and document 2. Okay. And let's check the first document, the third document. Okay, for the C1 and C3, what is the Jacob similarity? You see, R1 is the same, right? And R4 is also the same. So their similarity should be 0.5, right? Because we only count 1, 1 and 1, 1. They are 2 the same. And for their union, for the union you have R1, R2, R3, R4, R5. We didn't count R5. Okay, because they are 0, 0. We just ignore it. Okay, so actually their union is 4 and the intersection is 2. So the Jacob similarity is 0.5. Okay. And how about the signature similarity? Check S1 and S3. You see S1 and S3 in their first computation, their mean hash value are the same, right? And the second, the same. The third, okay, different. So their similarity will be 2 to the 2/3, right? They look very close, right? And we check the third pair, the second and the third document. For the second and third documents, you can see for these two columns, their similarity, Jacob similarity will be 0.25, right? And how about their signature similarity? For the second and the third column, there are no any pairs, no pairs. They are the same, so their similarity will be 0, very low, right? So although they have a gap, but I think they are roughly similar. Okay. So this means you can use the signature to estimate the similarity between the two documents, and the scores are approximate close. Okay. Any problems? Okay, so this slide shows us algorithm to summarize the above steps. Okay, so first we commute the loads of the polymetric rendering, and here we have mean hash functions. Let's try to find the first. You just check from the loads. Okay, according to after your computation, you just check from the first row to see which is the first one appear. And we just repeat the first and the second step, okay, several times to see how many signatures, how many mean hash values we want to generate. We just repeat several times. And finally we generate the signature vector. Okay, then we can compute the similarity between two documents, but just by using the signature vectors. Okay, so this we call the mean hash. Okay, so alright, so but although the idea is simple, okay, and very interesting, but the implementation will be not like this. Okay, so suppose you have 1 billion rows, 1 billion shingles, or so many. And if you want to pick a computation, to perform a computation of the 1BS is a very, you require a lot of memory and spend much time to do this. Okay, so it's impractical to implement a computation for if you have so many shingles here. Okay, so here we will alternatively we use another way to approximate the computation. We just pick 100 hash functions, and for the hash functions we will do an implementation in this way. Okay, here is algorithms, but I just show you the examples here how to implement it. Okay, so here we have 2 documents, and here are the shingles, 5 shingles. We want to generate the mean hash signature by these 2. Okay, only 2 mean hash values. Okay, so it means we have to prepare 2 hash functions here. The 2 hash functions will use to, means we will use it to do the computation by using the hash function. Okay, and each one will generate 1 hash value. Okay, if we have 2, we'll generate 2 hash values as our signature. Okay, so let's start to do the generation. Okay, so first you initialize. Here is we call it the slots. Here it means the first one for the first document and the second document, and here is initialized as infinity, very large, very okay. Because we want after each we will only keep the smallest hash values. Okay, so but initialization is like this. Okay, it's the first document signature and the second document signature here. Okay, let's start from the first row and the second row, third row. We just follow this way. Okay, so for each row, x from 1 to 5, we compute the hash values according to the hash functions. Okay, so first from the first row, so your x will be 1. Okay, we just put h1. The computer this value is 1. Use this function. When x is 1, okay, x more than 5, so you get your hash value is 1. Okay, so 1 is you just check 1 is smaller than your current value. Okay, so you can replace 1 with the infinity here. And for the second computation function, G1, you use the second function here. Okay, you can get is hash value is 3. Okay, so 3 is also smaller than the infinity. Okay, so I place it in the slot. Okay, sorry, you have to also check in C1 is first row is also 1. If it's 1, so I can use it to replace the original value. Otherwise, for example, in C2, for C2 documents, you see it's 0. The C2 documents, its first row is 0. So even I already get its hash values 1 and 3, but it's inactive for C2. So C2 will not be replaced. Okay? Okay, any problems? Okay, we'll just repeat to the second row. The second row is here. We take the second row to calculate the mean hash values 2 and 0. And also you have to check in the second row, the C1 is 0, so we cannot apply this hash value here. But for the second document, it's 1. Okay, so I can use the 2 and the 0 compare with their original values. If it's smaller, I can replace here. And we just repeat on for the third row. Okay, you find the hash values 3 and 2, and you can check. Okay, for the third row, they are both 1. Okay, so we can compare. Try to use the hash value, but the 3 and the 2, 3 is smaller than 1. No, it's bigger. Okay, so I cannot replace it. But 2 is smaller than the 3. Okay, so that's why I replace 3 to be 2. Okay, and but compare with your document 2 here. 3 is bigger than 2, so I cannot replace it. And the 2 is also bigger than 0, so I just keep the original value because I only keep the smallest one. Okay, so I just follow this way until the final rows, and this is our final result. The final result will be the hash value, the signature of the document 1 is 1, 2, and for the second document, the signature of the new hash is 0, 0. Okay, so no problems. So with this way, we don't perform computation. No? We just scan once. Just scan from the first row, second row, third row, to generate your final in-cache signature. Okay, so let's take a break. Okay.